Welcome back to leveling up your Arduino code, or leveling it down, however you want to see it. This time we're going to talk about timer interrupts. If you're not familiar with writing directly to registers or how interrupts work in general, I recommend watching the previous 2 episodes. Microcontroller timers are like kitchen timers. They continue to count while you're off doing other things, like prepping a salad or explaining how interrupts work. When they go off, you need to stop what you're doing and go get that casserole out of the oven before it burns. Excuse me. If we look at the various interrupt vectors available to us in the ATmega328P, we see that there are 3 different timers labeled timer 0, timer 1, and timer 2. Scroll down to the register map and we see that each timer lives in memory as a special function register. Timer 0 is TCNT0, which stands for timer counter 0. Timer 1 is TCNT1, and notice that it takes up 2 bytes in memory. Finally, timer 2 is TCNT2. Let's see how these timers get automatically incremented without any code. Each of these 3 timers can be directly or indirectly connected to the system clock. The system clock is a square wave that is produced internally in the microcontroller based on your settings. It could be generated inside the microcontroller itself or from a connected oscillator or crystal. The system clock is vital to the operation of almost everything in the microcontroller. The Arduino Uno, for example, has a 16 MHz crystal connected to the microcontroller. The 328P generates a 16 MHz square wave from this, which is used to feed many functions, including our timers. The timers can be connected directly to the system clock, which means the value in the timer register increments once every 62.5 nanoseconds, which we get by dividing 1 over 16 MHz. The system clock is also fed into another piece of hardware known as a prescaler. The prescaler divides the clock by producing a pulse every 8 system clock cycles or every 16 clock cycles, however we define the prescaler. Let's say that we don't have a prescaler set. Every time the system clock pulses high, each of our timers increment by 1. We'll be focusing on timer 1 in this example. Let's say we set the prescaler to 8. Now, timer 1 increments only once every 8 system clock pulses. As you can see, we can play with these prescaler values to adjust how fast each of our timers counts. Now, the question is, what do we do with these counting timers? Timer 0 and timer 2 are both 8 bits each, which means they count from 0 to 255. Note that once a timer reaches its maximum value, it starts over again from 0. Timer 1, however, takes up 2 registers in memory, so it's actually 16 bits, meaning it can count from 0 to 65,535 before rolling over. Each timer can generate 1 or more interrupts. We can write a value in another register so that when one of the timers equals that value, it throws an interrupt. This is known as a compare-match interrupt, and all of the timers can make this interrupt happen. Similarly, we can tell the processor to generate an interrupt when each of the timers overflows, which means rolls over from its max value to 0. Finally, timer 1 can be configured to store its current count to another register whenever an external event happens on a pin. This is known as input capture. If you are working in Arduino, note that several functions rely on timers to operate. So if you begin playing with timer 0, the delay, millis, and micros functions will no longer work properly. The same applies to the servo and tone functions for timers 1 and 2. The analog write function uses all 3 timers in the Uno, but which timer depends on which pin you're using. For example, if you want to manually control timer 1 for other things, you probably shouldn't use analog write on pins 9 and 10. Let's see how these different interrupts might be generated using timer 1 as an example. As we run our program and time progresses, we'll see the value in timer 1 continually increasing at each system clock pulse or at a pulse from the prescaler. One thing that happens is each time timer 1 is incremented, its value is compared to the value in the output compare registers. For example, we might have 65,531 stored in the OCR1A register. When timer 1's value equals that number, a compare match interrupt is generated. In this case, the interrupt source would be timer 1 comp A. Next, Every time the timer 1 counter goes from its max value to 0, an overflow interrupt is generated, which is known as the timer 1 OVF source. Finally, if we have the input capture set up for timer 1, whenever a logic level change occurs on a specific pin, such as the ICP1 pin in this example, which is port B pin 0, an input capture interrupt is generated. At the same time, the value of the timer 1 counter is stored in the ICR1 register, so you can refer to it later if you want to see exactly when that event occurred. Compare and overflow interrupts are useful if you want to, say, toggle a pin or read from a sensor at precise regular intervals. Capture interrupts are great if you need to measure the time between pulses or measure the frequency of an unknown signal. To see how to set up timer interrupts, let's look at an example that is the classic Blinky program. To do that, you will need an Arduino with an ATmega328P, such as the Uno or Red board. We'll be using pin 13 this time, as it's already connected to an onboard LED. Notice that Arduino pin 13 is actually port B pin 5 on the 328P. We'll start with this simple example. Here, we set pin 13 as an output and tell it to go to 5 volts, wait 500 milliseconds, go to 0 volts, and wait another 500 milliseconds. If we run this, we see that it has the effect of blinking the LED at a 1 Hz rate. First up, let's change this to be direct register writes. Instead of pin 13, we'll use PB5. This is another unique number that's defined by the AVR libraries. PB5 refers to bit 5, so we can use it when we're dealing with the data direction and port registers. Delete pin mode and change it to DDRB, vertical bar equals, 1 left shift LED pin. Notice that we're using DDRB here. We're using port B instead of port D like last time. Delete everything in loop and write port B caret equals 1 left shift LED pin, followed by delay 500. This flips bit 5 in the port B register, which turns the LED from on to off or vice versa. The processor then does nothing for 0.5 seconds before flipping the bit again. Run this again and you'll see that the LED blinks the same way. Take a look at your 328P datasheet. We'll use timer 1 as it can count the highest and it's not used by delay in millis in Arduino. Go to the register description section under TC1. We don't need the TCCR1A register for what we're doing, but we will need to reset all of its bit values to 0, as Arduino has a habit of setting these by default for the analog write functions. Note that you can set up output compare pins, which allow you to toggle pins without calling anything in code. This can be useful for things like pulse width modulation, and it's how analog write works in Arduino. We won't cover that here though. Scroll down and take a look at TCCR1B. We don't need the input capture or waveform generation mode bits, but we do need to be concerned with the prescaler select bits. Notice that we can disable the prescaler or set it to 8, 64, 256, or 1024 to divide the clock. What we'll be doing is setting the timer 1 counter to 0 and letting it count up from there. We'll also set the output compare register 1A to some value that's less than the timer 1 max value of 65,535. When timer 1 reaches this value, a compare A interrupt is generated and we'll execute our interrupt service routine. In the ISR, we'll reset the timer 1 value to 0 and toggle our LED. Timer 1 will continue counting up, and when it reaches the value in our compare register again, another interrupt will trigger. We just repeat this process forever to get a blinking LED. Ideally, we want the time between compare interrupts to be 500 milliseconds. So we need to find which value to load into the output compare registers to make the time between interrupts be 500 milliseconds. To do that, we need to do a little math. We know that the time it takes for one cycle of the clock with no prescaler is 1 divided by the frequency, or 16 megahertz. This means the period is 62.5 nanoseconds. With a prescaler, we divide the clock speed, or multiply the period. For example, with a prescaler of 8, we see that the timer will now increment every 500 nanoseconds. We want to see how many timer counts is needed to get to 0.5 seconds. With no prescaler, we can divide 0.5 seconds by 1 over 16 megahertz to get 8 million counts. Well, 8 million won't fit in our 16-bit counter, as that can only store up to about 65,000. Okay, what about a prescaler of 8? Well, we can multiply 0.5 seconds by 16 megahertz and divide that result by the prescaler to get the number of timer counts it'll take. For a prescaler of 8, we see that it'll take about 1 million. Still too much. Let's check the other available prescaler values of 64, 256, and 1024. 125,000 is still too much, and 7,812.5 isn't a whole number, which means the timing will be slightly off. That gives us a prescaler of 256, which will take 31,250 timer 1 counts to give us 0.5 seconds. Perfect! So we'll load this value into the output compare register, and whenever timer 1 reaches it, an interrupt will happen. So now, we know that we need to set the CS10, 11, and 12 bits to binary 100 to select a 256 prescaler. Keep scrolling down. We don't need to worry about TCCR1C. Because timer 1 is 16 bits, it actually takes up 2 registers, so the lower 8 bits and upper 8 bits are in separate registers. Lucky for us, the AVR libraries help us out, and we can just write a single value to TCNT1 instead of having to worry about the upper and lower bytes. We don't need the input capture registers, but we do need to write our target number into the output compare registers. On every timer 1 increment, its value is compared to the OCR1A and OCR1B registers. If the values are equal to either one of those, then an interrupt is generated. Keep scrolling down until you find the timer counter 1 interrupt mask register. These bits control the individual interrupt enables for the various functions associated with timer 1. We just need to set the output compare A match interrupt enable bit. Back in our code, let's create some constant variables to hold our initial timer value and our calculated compare match value. Write const uint 16t t1 load equals 0. Then write const uint 16t t1 comp equals 31,250, which is our compare value. We make it an unsigned integer with 16 bits, as that constant is too big for a single byte. In setup, after we set our LED pin as output, write TCCR1A equals 0 to reset the timer 1 control register A to its default value. Under that, write TCCR1B vertical bar equals 1 left shift CS12. Then TCCR1B ampersand equals tilde open parentheses 1 left shift CS11 close parentheses. And TCCR1B ampersand equals tilde open parentheses 1 left shift CS10 close parentheses. These set the CS bits to binary 100 to select a prescaler of 256. Write TCNT1 equals T1 load to load the actual timer with 0. Under that, write OCR1A equals T1 comp to store our match value into the output compare 1A register. Then TIMSK1 equals 1 left shift OCIE1A to set the output compare interrupt enable bit for timer 1 compare match A. Finally, write SEI to enable global interrupts. Delete our port B bit flip in loop, leaving the delay 500 to pretend the processor is doing something important. Under loop, write ISR, open parentheses, timer 1, comp A, vect, close parentheses, open curly brace, to create our interrupt service routine for the timer 1 compare match A vector. In that, write TCNT1 equals T1 load to reset timer 1 to 0. Then, port B caret equals 1 left shift LED pin to toggle our LED, and with a curly brace, and upload this code. Not surprisingly, our little LED continues to blink at the same rate. Just to show you that we really are blinking at a rate of 1 Hertz, I've set up this oscilloscope, and as you can see, it's about 1 second measured from one rising edge to the next. Using timer interrupts are great for when you need to run pieces of code at exact intervals. We can make this even slightly more efficient by using the clear timer on compare mode. All this does is tell the hardware to automatically reset the timer back to 0 whenever a compare match interrupt happens. I know we skipped the TCCR1A register initially, but let's go back to it in the datasheet. Scroll down to the waveform generation mode table. There are many fun ways to control how the timers interact with pins, but we want mode 4. If you look at this row, you see CTC, which means that the timer is reset to 0 whenever it reaches the top. In this case, the top is set at whatever value is in the OCR1A register, our compare match value. To use this mode, we need to write a 1 to the WGM12 bit. Funny enough, the WGM12 bit is actually in the TCCR1B register, so we just need to update it there. In our code, just before we set the prescaler, write TCCR1B ampersand equals tilde, open parentheses, 1 left shift, WGM13 close parentheses to make sure it's cleared, and write TCCR1B vertical bar equals 1 left shift WGM12 to set the WGM12 bit. In our ISR, delete the line where we reset TCNT1. Let's run this code. Sure enough, we're still blinking at a 1 Hz rate. Using CTC mode only saves you one instruction, but when you need to make your ISRs as short as possible, every instruction counts. There are many more ways to use the interrupts that we didn't cover here, like input capture or overflow. If you want to see more fun videos like this, make sure you subscribe to our channel. Good luck and happy hacking! We can make this. Oh, that was T. Similarly, don't make this word bother me again. Distance between 2 points, and when 2 trains connect in Cincinnati, how fast are they going? Awkward pauses. Thumb. That's a real word. That wasn't right, by the way. No. 1 second measured from